All right, so today we're going to continue with the second part of our introduction to modular arithmetic. Specifically, last time we looked at Fermat's little theorem, Euler's theorem, the special SP, SN, GN sets. So today we're basically going to continue with that, develop a couple more theorems like Wilson's theorem, Bezout's theorem, and also discuss modular inverses and maybe a couple more advanced topics and look at a couple practice problems and examples. So I guess let's go ahead and get started. So let's just do maybe a quick review of the material that we saw last time. So I guess I'm sharing my screen in here. So let's just quickly recall what were some of the main ideas. So basically, we're looking at this special set, which we call SP, right? SP, and this is basically all the remainders mod P. So we had 1, 2, 3, 4, all the way until, P minus 1. And then I guess let's actually have more space in here, all the way until, P minus 1. And then we say that we have another set, ASP. And the interesting property about this set is that it's going to be A, 2A, 3A, 4A, all the way until, P minus 1A. And the interesting thing that we discussed last time is that these two sets, they're the same set, right? So basically, we saw that the set A is going to be the same as the set. So basically, the set SP is going to be the same as the set ASP. As long as A and P are good numbers, right? So A and P equals 1. So basically good pair. So what does it mean for A and P to be have the greatest common divisor 1? Well, the only divisors P has is 1 and P itself. It means that A is not a multiple of P. So basically A is not of the form KP, where basically P doesn't divide A. So these are all kind of like equivalent conditions, or A is not congruent with 0 mod P, right? So these are all saying basically the same statement. So yeah, let's just keep them like this. So as long as, any of these conditions are satisfied, this is always the case. And in addition to that, I guess, what is actually, one of the main observations in here? Well, look at this. If these two sets are the same, right? If these two sets are the same, then what does it mean? Well, it means there's always going to be some element, Ka, there's always going to be some element in here. So basically, if these elements are the same, there's going to be some matching between these elements. Like basically, each element in here is going to correspond to one element in here. So for example, there's always going to be some element in here that's going to go into one. Maybe we can call this element K. Ka. Okay, so now what is going to be special about this element Ka that has the same remainder as 1? Well, if you look at this, what this is saying is that basically Ka, or actually let's use purple color. So what this is saying is that Ka is going to be congruent with 1 mod P, right? So Ka is going to be congruent with 1 mod P. Well, so this is basically true for any number A. So for any A that is good to P. So maybe I should actually write this. So for any A, so for all A and A such that, right? So such that A and P is a good pair, A and P is equal 1. So good pair. So I should write good pair. So as long as you have a good pair, what do we have? There exists some K such that Ka is going to be congruent with 1 mod P. Now, what does it mean for Ka to be congruent with 1 mod P? Basically, what this means is that K is called the modular inverse. So oftentimes we write it like this. We write that K is equal to A minus 1 and is congruent with 1 over A mod P. And this is called the modular inverse. So this is a modular inverse. Now, what is so interesting about modular inverses? Well, I guess when I write, so when you see the notation A minus 1 or 1 over A or K, this is all the same numbers that give you 1 mod P. Now, what is interesting about this number? Well, this number is going to be, well, first of all, it's unique, right? There is going to be only one K in this set from 1 to P minus 1. So if I look at like 1, 2A, 3A, 4A, there's going to be only one K that goes in there. Why is this modular inverse unique? So basically a couple points. So it is unique unique, and always exists. So why is the modular inverse unique? Well, let's say that we had two modular inverses, right? So we had like Ka, and maybe we also had some Sa, and let's say that Sa also goes into 1. Well, then what is the interesting property here? Let's say that, Ka, so basically, if not unique, then what is the problem in here? Let's say that, Ka is going to be congruent with some Sa mod P. But now look at this. A and P are good numbers, right? So if A and P are good numbers, I can always come and simplify A on both sides. And then what would I get in here? I would get that basically K is going to be congruent with S mod P. So basically, but now look at this. K and S are numbers between 1 and P minus 1, right? So basically, the only way this can happen is that if K is equal to S. So it means that it means that it's unique because it means it's the same number, right? Like otherwise it's not possible. You cannot have like K different. So if they're not unique, then K cannot be equal to S, right? Because you pick two different numbers, but then you get that K is congruent with S, so you get that K is equal to S. So this is a contradiction, right? Because this thing in here cannot happen, right? So you cannot have K to be congruent with S. So this is a contradiction. Okay, so we get that the modular inverse is always unique and it always exists. All right, so I guess let's try and understand a little bit more about this modular inverse. So maybe we can look at like some simple examples, right? So let's maybe start with some simple sets. So let's look at let's say the set S7, right? Which is the remainders mod 7. So these are going to be 1, 2, 3, 4, 5, 6, right? So we're looking at this, mod 7. Okay, then here is an interesting property. Well, what is the modular, what should I multiply 1 by to get, 1 mod 7? So let's look at this number. So if I multiply 1 times something is going to be congruent with 1 mod 7. And then I'm gonna take 2 times something is gonna be congruent with 1 mod 7. So let's try and figure out what should I multiply each number by. So take 2, 3, 4, 5, and 6. Well, one thing we notice is that if I multiply 1 by itself, then I just get 1 mod 7. 2 I can multiply, well, 1, no, 2 times 2 is 4, 2 times 3 6, 2 times 4, right? So if I do 2 times 4, I see that this is congruent with 8 and this is congruent with 1 mod 7. So this immediately tells me that 4 times 2 is also going to be congruent with 8. It's going to be congruent with 1 mod 7, right? And then additionally to that, well, what else do we have? So we have 3 times, well, I cannot use 1, 4, or 2 because, the modular inverse is unique and the modular inverse of 1 is 1. The modular inverse of 4 is 2. The modular inverse of 2 is 4. So 3 can be paired with 3, 5, or 6, right? So if I look at 3, I see that 3 actually gets paired with 5. 3 times 5 is going to be 15. It's going to be 15, which is also going to be congruent with 1 mod 7, right? Okay, and then what about 5? Well, if 3 goes with 5, then 5 has to go with 3, which is going to be 15, which is going to be congruent with 1 mod 7. And then what about 6? Well, 6 is going to go with itself. So we see that this is 36, and it's also congruent with 1 mod 7. Okay, cool. So actually we noticed something very interesting in here. So first of all of these modular inverses, they sort of go in pairs, right? So we see that, 2 goes with 4, 3 is going to go with 5, 6 is going with itself, and 1 is going with itself. So actually there is a question. Is this always the case, right? Well, also look at this. If you have a modular inverse, so let's say that I know that 2 is the modular inverse of 4, right? So basically, if I look at the set, what are going to be the modular inverses of 4? So let's say that I'm looking at the set 4 minus 1, which is, 1 over 4. Well, what is this? Well, this is basically all the numbers, k, such that 4k is going to be congruent with 1 mod p. So basically all the numbers that give me 1 mod p. So let's look at like what are some of these numbers that satisfy this property. Well, one number, for example, is 2, right? So for example, if I do 2 times 4, I know that this is congruent with 8. I know that this is congruent with 1 mod 7, right? Okay, but besides 2, one other thing I can do, because I'm looking at this stuff mod 7, if I found 1, I can always add 7 to it or subtract 7. So for example, if I look at 2 plus 7, 9, right? 9 is also going to be a modular inverse. Why is that the case? Because, well, look at this. I'm going to have 4 times 9 is going to be 36, which is, congruent with 35 plus 1, which is congruent with 1 mod 7. More specifically, if let's say that I had a modular inverse, so let's say that I had 4, let's say that I had 2, and I look at the number 2 plus, 7k. Well, 7k is always congruent with 0 mod p. So actually, if I take 2 and I add any multiple of 7 to it, or subtract any multiple of 7 to it, it's still going to be a modular inverse. Why is that the case? Because, well, if I take 4 and I multiply it by 2 plus 7k, well, this is going to be congruent with 8 plus 4 times 7k, which is going to be congruent. Well, this part is just congruent with 0. So this is going to be just congruent with 8, which is congruent with 1 mod 7, right? So mod 7. So what do we see is that actually 4 inverse or 1 over 4, this is actually a set. It can be any of these numbers that are like modular inverses, mod 7. So for example, 2, 9, I guess if I keep adding 7 to 9, I'm going to get I guess it's going to be, for example, 16, right? So let me add the numbers in here. So for example, 16. If I add another 7, for example, it's going to be 23. And then, for example, 72. All of the numbers of the form 7k plus 2 are going to work in here, right? And I can also subtract 7. So for example, if I look at like minus 5 or like minus 12 or like all the numbers like this, all these numbers are also gonna work, right? So yeah, basically the set of 4 inverse is like it's multiple numbers. But if you look at if you restrict it from numbers from 1 to 7, or sorry, between 0 and 6, right? Because 7 is technically 0. Then if you look at like this set, that's only, you don't let the remainders repeat, because clearly 2, 9, 16, they all have the same remainder too. So if you only pick number, you don't let the remainders repeat, and you pick all the unique remainders between 1 and 6. Well, what do you see is that, they all sort of like go in pairs. The only exception is that the first gets paired with the first to give you 1, 6 gets paired with 6. So basically the modular inverse of 1 is 1, the modular inverse of 6 is 6, but all the other modular inverses, they sort of go in pairs. All right, okay, so that's basically, it's actually quite interesting. So let's see that actually if that's always the case. Actually, before that, we actually have one more number in here. So we also know, if you guys remember from the previous lecture, we have Fermat's little theorem, right? So Fermat's little theorem, what does it say? Well, it says that, so let's write it down. So I have, a to the power p minus 1 is going to be congruent with 1 mod p. So for example, in this case, a to the power 6 is going to be congruent with, 1 mod 7, all right? Okay, so now as long as a and 7 is a good pair, a and 7 is a good pair. So I can take actually any number and raise it to the power 6. Well, but now what do we have in here? So if a and 6 gives me 1 mod 7, look at this. I can rewrite this as, a times a to the power p minus 2, right? So I can rewrite this as like a times a to the power I guess a to the power 5, right? It's going to be congruent with 6. It's going to be congruent with 1. So now look at this. Well, what does this mean? Well, if my number, for example, is 4, right? If this number was a 4, then this would be a 4 to the power 4p plus 2. So basically, if I call this number k, so basically what we see is that this number in here, it's basically the modular inverse of a. It's a, which is basically 1 over a. Because if I take this number and I multiply it to a, I get 1 mod p. Right? So if I made a to be equal 4, then this number would be the modular inverse of 4, because when I take this number and multiply it with this number, I'd get minus 1. So okay, so if I make a to be 4, I basically get 4 to the power, 5. So basically 4 to the power, p minus 2 is also going to be a modular inverse, right? So basically there's like also another way to get modular inverses using Fermat's little theorem. All right, cool. So now that we get a little bit of intuition about this modular inverses, let's go in a little bit more detail and look at them. Okay, so basically we got that this modular inverses, they always sort of exist. Actually, before we go any further, let's look at an even simpler example. So a couple simple properties that we discussed was like the addition, multiplication, subtraction of modular arithmetic, right? So we had stuff like if a is congruent with b mod, let's say n, and if c is going to be congruent with b mod n, then one thing I can do is I can basically add them. For example, I can do a plus or minus or multiplied by c is going to be congruent with b plus minus multiplied by d mod n. In addition to that, I can also raise to powers, right? So I can say a to the power k is going to be congruent with b to the power k. mod n. But now another thing I want to look at is like what happens when you take square roots. So basically, let's say that I have something like this, that a squared is going to be congruent with 1 mod b, right? Then the question is, can I come and can I take square root of this? Can I say that, if I take square root of this and take square root of this, can I say that a is going to be congruent with plus or minus 1 mod b? Let's see if this is the case. Well, what happens when I have that a is congruent with 1, a squared is congruent with 1 mod p? It means that they have the same remainder, right? So p has to divide their difference. It means that, p is going to divide their difference. So this is basically the idea of the square root. So let me move this a little bit down. So let's write it like this. So square roots SQRT with modular arithmetic, right? Modular arithmetic. Okay, so what happens when we do square roots with modular arithmetic? Well, I guess in here, because these two have the same remainder, p has to divide their difference. So I can just like write that, that p. So in here, I'm going to have that, p is going to divide their difference, a squared minus 1, which is actually equal to a minus 1 times a plus 1. So actually in here, we get some interesting properties. Basically, we get that there's two options. Because p is a prime, p doesn't have any divisors in it. Basically, p either needs to divide this or both of them. If p were to divide both of them, then it also needs to divide their difference, and it needs to divide 2. So if p needs to divide 2, basically there is this simple property here. If p divides x and if p divides y, then from here you can say that p is also going to divide x plus y, but p is also going to divide x minus y. So in here, let's say if p were to divide both of them, that would be a problem. What would be the problem if p divides both of them? Well, if p divides, let's say that p divides a minus 1 and p divides a plus 1, then, well, it means that p needs to divide their difference and it needs to divide their sum, right? So so you imagine x is this thing and this is x and this is y, then what's happening? Well, p needs to divide their sum, which is going to be 2a, but p also needs to divide their difference. So basically, this minus this, for example, which should be basically 2. So the only way that's possible is that if p is equal to 2, right? But let's look at the case where p is greater than, let's assume in our case p is greater than 2. So let's just skip this part in here. Let's not look at this. Well, I guess then there's going to be only one option. P either divides the first or the second. So you either have that p divides a minus 1 because p is a prime, or p needs to divide a plus 1. Well, what does this mean? Well, this means that a is going to be congruent with 1 mod p, or it means that a is going to be congruent with minus 1 mod p. Okay, so what is one interesting property that we get in here? Turns out that if you have that a squared is congruent with 1, turns out you can also say that a, so you can do square root, and you can say that a is going to be congruent with plus or minus 1 mod b. So basically, we can come and we can take square roots, right? Now, an interesting property in here is that there is nothing special about, like if I were to do, I can also redo this thing with replacing 1 with b, for example. So let's say that, a squared was congruent with b squared. Then I can write, b squared here, and I can write a minus b, a plus b, and I can write a minus b, a plus b, and then I can say a is going to be congruent with b, or a is going to be congruent with minus b mod p, right? So, and then basically I would have this, that a is going to be congruent with plus or minus b mod p. So basically, if you do stuff mod p, it always works like this. So basically, this is the special case, but, more generally, you also have if a squared is going to be congruent with b squared mod p, then basically what you can do is you can also come and take square root, and you can say that a is going to be congruent with plus or minus b mod p. Okay, so this is, modular arithmetic. When you have like the two squares are congruent, you can come and you can take basically square root. So can do square root. So what this means is that, I can do a square root in order to get this, right? But now the question is, how about what if I try to do the exact same thing, but now instead of working mod p, I try to work mod n? So let's look at like this other example. So if I tried to work mod n, let's say that, that a squared was congruent with b squared mod n. Then what would happen in here? Well, it means the two of them have the same remainder mod n, so n needs to divide their difference. So n needs to divide, a squared minus b squared, which is going to be a minus b times a plus b. But now here is the problem. So normally, if this was a prime number, then prime number either needs to divide this or it needs to divide this, right? But in here, I cannot do this step because, I could have had that n is made out of some CD where, C is going to divide this and D is going to divide this. So basically, I can no longer say that n divides a minus b or n divides a plus b. It's totally possible that a part of n is going to divide this and another part of n is going to divide this. It wasn't the case here because I couldn't split p in two chunks, right? To have part of p divides this, part of p divides this, because p is a prime. But if n is a composite number, this wouldn't work anymore, right? Instead, what I would have is I would have that like some number c is going to divide a minus b, and some number d, or maybe some number d, is going to divide a plus b. But then, well, what does this mean? Well, this is going to mean that a is congruent with b mod c. So, or a is going to be congruent with minus b mod d, right? So basically the SQRT doesn't work in here. So SQRT square root SQRT doesn't work mod n, only mod p, right? So the only way taking square roots works is if you do it mod p. Okay, cool. So now that we have an understanding of modular arithmetic, and square roots, what are like some tricks we can do with it? So I guess one simple thing we can do right away is if we try to use Fermat's little theorem, right? So from Fermat's little theorem, we know what? We know that, if A and P are good, right? So if A and P are a good pair, then I can just say right away that a to the power p minus 1 is going to be congruent with 1 mod p. So I can do is I can come and I can take square roots. So I'm going to get that a to the power p minus 1 divided by 2 is going to be congruent with plus or minus 1 mod p, right? Okay, so this is, for example, one application of taking square roots. So you can very easily, so for example, if you had mod 7, right? And if you're curious, what is, you'd have 2 to the power 6 2 to the power 6. So let's say you had 2 to the power 6 is going to be congruent with 1 mod 7. Then one thing you can check right away is you can look at, say, 2 to the power 3, and it's going to be congruent with plus or minus 1 mod 7. And actually, in our case, you can check, you can plug in, in this case, you can plug in, like literally compute the numbers. So 2 cubed is going to be 8, which is going to be congruent with 1. So you see that 1 is an option here, right? Yeah, so this helps you like very easily get plus or minus 1 mod p. All right, cool. Let's maybe look at like some other bigger examples. So another bigger example is, if you wanted to get, for example, 2 to the power 12, right? So 2 to the power 12 is going to be congruent with 1 mod 13. Well, then one thing this tells us right away is that if I take square root 2 to the power 6, it's going to be congruent with plus or minus 1 mod 13. Now, what is 2 to the power 6, right? So this is going to be, I guess, 64, right? So see, if I take 64 and I divide it by 13, so I divide by 13. Yeah, I get that 2 to the power 6 is actually, this is going to be congruent with 64, which is going to be congruent with minus 1, which is, 65 minus 1. 65 minus 1, which is congruent with minus 1. Mod 13. All right, cool. So we see that basically, yeah, this idea of like taking square roots always works. All right, so now I guess let's get back to where we began with this special sets SP. So I guess what do we see in here? We see that if I have the set SP is equal to the set ASP, right, then it means that there's going to be some number in here that goes into 1, some number KA. So I'm going to get that K is going to be congruent with 1 as long as, A and P are a good pair. So basically this K, we call this a modular inverse. Now, the thing is, we don't know what number K we should pick, but this theorem tells us that this number exists. It's like we don't know how the numbers in here match to the numbers in here, but we know that this remainders in here are the exactly same remainders in here. So there is going to be some remainder in here, Ka, that's going to be exactly 1. Now, the theorem also states that this remainder is unique. So basically, I cannot have another remainder that also goes some other remainder that also goes into 1, right? Because if I had another remainder SA, so let's say that K is different from S, then I would have this KA is congruent with SA mod P, right? Because, and they're also congruent with 1, I guess I should say congruent with 1, right? So now if I simplify A on both sides, I'll just get that K is congruent with S, and I can simplify A because A and P is a good pair. I can always simplify when the numbers are good pairs. So if A and P are good pairs, I can always cancel A on both sides. So I get that K is congruent with S, but this would mean that K is equal to S, which is a contradiction because K is not equal to S. Okay, so we get that the modular inverse exists. All right, cool. So now I guess what can we do with this? I guess with the same thing also apply mod n. Turns out that you can do the same thing mod n as well, but yeah, we'll look at like mod n a little bit later. So for now, let's just focus on this. Okay, so now that given that we have modular inverses, actually, if we look at one example, we see that some numbers go in pairs. For example, if I look at like mod 7, I see that 1 gets paired with 1, 2 and 4 get paired, 3 and 5 get paired, and 6 gets paired with itself, right? So now here's an interesting question. Well, let's say that I had my set as P again. So yeah, so let's create our set as P. So if I look at the set as P, well, what are the possible remainders? I'm gonna have 1, 2, 3, 4, 5, all the way until P minus 1. Okay, so now let's see what is gonna be the modular inverse of each number in here. Well, if I'm gonna have some number, A in here, I see that, A. So if I look at, all these numbers, they're good numbers to P, right? They're all relatively prime to P. So if I pick any number A, I know that, if I look at the set SP and ASP, there's going to be some KA that goes into 1. So basically, A and K are going to be modular inverses. So basically, what I'm trying to say is that if there's some number A, there's going to be some number K, such that K and A are, modular inverses. Now, here's a couple questions. Well, can A also be paired with some other number S such that they're also modular inverses? And remember, we're working mod P, right? Mod P. And also the question is, can A be paired with itself? And does A even have a modular inverse? So, okay, from the beginning, we know that A always has a modular inverse, right? So we know that A has a modular inverse. Actually, here's another question. Can A be itself its own modular inverse? Can I also have that, can K be equal to A? Can A be its own modular inverse? So basically, I guess what I'm trying to say is that if you look in this case in here, right, so clearly I cannot have, A cannot go to two separate things. I cannot have AK is congruent with AS mod P, because in that case, I would cancel A and I would get that K is congruent with S mod P. But, K and S are K is not equal to S, and they're both between, P minus 1 and 1, right? So this is contradiction. So, A is going to have only one modular inverse. Now, the question is, can A be its own modular inverse? So can A basically be its own modular inverse? So can, A? So, yeah. Can A be its own modular inverse? So the question is, can you have like A squared is going to be congruent with 1 mod P? Well, we know that if this is the case, I can come and I can take square root. So there's two options. A is going to be congruent with 1 mod P. Or the second option is that A is going to be congruent with minus 1, which is basically congruent with P minus 1 mod P. So basically now, if A is only between 1 and P minus 1, you see that this case A is congruent with 1 mod P. It means that you're looking at the number 1. So basically, either you have two options. Either A is equal to 1, right? If A is congruent with 1 mod P, then A needs to be 1. If A is congruent with P minus 1, then A needs to be P minus 1. So we see that, the only way A can be paired with itself is if A is 1 or A is P minus 1. Otherwise, I'm always going to have that these numbers go in pairs, right? So like 2 is going to get paired with something, 3 is going to get paired with something, 4 is going to get paired with something, 5 and something is going to, so basically all the numbers, they're going to go in pairs, right? 1 is going to be paired with itself, 6 is going to be paired with itself, but everything else is going to be go in pairs. So this is actually the same that we saw for like mod 7, right? In mod 7, we saw that 1 got paired with itself, 6 got paired with itself, but 2 got paired with 4, 3 got paired with 5. Let's look at maybe one more example. So for example, if we look mod 11, right? So let's look at, mod 11. What are the remainders mod 11? So mod 11, I'm going to have, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? These are like the possible remainders, mod 11. All right, so if I look at 10, I know that, 10 times 10 is going to be congruent with 100, which is going to be congruent with 99 plus 1, which is going to be congruent with 1 mod 11, right? So, all right, so we're looking at, mod 11, which is a prime number. Okay, so I know what? I know that, 10 gets paired with itself. Similarly, I can say that 1 times 1 is going to be congruent with 1 mod 11. So I also know that, 1 gets paired with itself. But what are going to be their modular inverses of all the other stuff? Well, what about 2? Well, 2 times 3 is 6. 2 times 4 is 8. 2 times 5, 10. 2 times 6 is 12, right? So if I actually pair 2 and 6, I get 12, which is going to be congruent with 1 mod 12. Sorry, 1 mod 11, right? So, if I write 2 times 6 is going to be congruent with 12, which is going to be congruent with 1 mod 11. All right, so I get that, 2 and 6 are modular inverses of each other because they give me 1 mod 11. Now, what about 3? Well, 3 actually with 4 gets paired, right? So if I look at 3 and 4, it gives me 12 again. So if I look 3 times 4 is going to be congruent with 12, which is also going to be congruent with 1 mod 11. So 3 and 4 are modular inverses of each other. Okay, so now I keep going. What about 5? Well, 5 times 7, 35. No, 5 times 8, 45 times 9, 45, which is 44 plus 1, right? So 5 and 9 go paired together. So if you look at, 5 times 9, you see that this is going to be 45, which is going to be congruent with 44 plus 1, which is congruent with 1 mod 11, right? So, okay, I got that 5 is paired with 9. And similarly, I guess 7 and 8. 7 and 8 is going to be 56. 7 times 8 is going to be congruent with 56, which is congruent with 55 plus 1, which is just congruent with 1 mod 11, right? Mod 11. So we got that, 7 and 8 are also paired. So this is very interesting. Turns out that if you take all the remainders from 1 all the way until p minus 1, they all go in pairs. So for example, 2 and 6, 3 and 4, 5 and 9, 7, 8, except the first and the last, right? So basically same story that we got in here. All the remainders go in pairs except the first and the last. Okay, so now here's an interesting question. What would happen if I were to take all these remainders and multiply them, right? So if I take all the remainders and I try to multiply them and I write 1 times 2 times, so basically if I multiply all the remainders, I would get, p minus 1 factorial, which is going to be congruent with 1 times 2 times 3 times 4 times 5 times 6 times 7 times, p minus 1. And what is this congruent to? Well, now what you can see is that you can pair 2 with some of its pair, and they're going to give you remainder 1. So you can cancel this with this. Maybe you can pair 3 with... So basically what I'm saying is that you pair 2 with its modular inverse, maybe some number in here. So you can cancel both of them. Pair 3 with some modular inverse. So you can cancel both of them. Pair 4 with its modular inverse, you can cancel them. Pair 5 with its modular inverse, you can cancel them. So basically all the modular inverses go in pairs, so they all get canceled. The only modular inverses that don't have pairs are 1 and p minus 1. So, I mean, 1, you can just forget about this. It doesn't do anything. So basically you get the entire thing is just going to be congruent with p minus 1, which is going to be basically congruent with minus 1 mod p. So now this thing here, it's called Wilson's theorem. So basically you get this. And also, if you look at just this and this, you can simplify it. And you can write it as, p minus 2 is going to be congruent factorial, right? So if I cancel a p minus 1 on both sides, so basically you get that this entire thing is congruent with minus 1. And all of this p minus 2 factorial is going to be congruent with 1 mod p, right? So it's going to be congruent with 1 mod p. And, p minus 1 factorial. P minus 1 factorial is going to be congruent with minus 1 mod p. And this is happening only for prime numbers. So this thing in here, this is called Wilson's theorem. So let's just write it down here, Wilson theorem. So basically Wilson's theorem says that, if you take all the numbers from 1 to p minus 1 and you multiply them, you just get that it's congruent with minus 1, which is p minus 1. And if you actually skip, you avoid, you take all the numbers except the last one, then basically it's saying that all of them are going to cancel in pairs to give you 1 mod p. So when you take the entire product except the last one, they're going to give you 1 mod p. Okay, cool. So yeah, so this is Wilson's theorem. Hopefully it's clear. And this is, a way to check if a number is prime. Okay, now what can we do next with this information, with this modular inverses? Well, it would be a good question to ask, can we do similar stuff, not only, mod p, but also, mod n. Can I basically apply the same results, and can I get modular inverses, mod n? Turns out that it doesn't quite work mod n. It only works mod p. So basically, if I try to do this thing mod n, right, what would I have? So if you look at the stuff mod n, so if I try to do this mod n, right, so if I were to do, let's say I had, so I look at the set Sn, which is basically, 1, 2, 3, 4, 5, 6, all the way until, n minus 1. Well, then remember that I need to take A and N to be a good pair, right? So basically I want good pair. If they're not a good pair, then none of this would work. So, okay, so if they're a good pair, I can also look at the set ASN, which is basically going to be A, 2A, 3A, 4A, all the way until n minus 1A, right? And then what do I know? I know that if they're a good pair, then basically the set Sn is going to be congruent with the set ASN, right? So if you have a good pair, you can always get this. And well, we also had that this is true for like SP and SP. And we also know that this is true if I take only the good numbers, right? If I were to take GN and GN, this would also work. Okay, so if I have this thing in here, then what is one thing I can say right away? Well, clearly there is gonna be some number in here, some number Ka, that's gonna go into 1 because these two sets are the same sets. So it turns out that the modular inverse always exists. So if A and N are good, right? Good pair, then what can I say from here? Basically, there is gonna exist a K such that Ka is gonna be Ka is congruent with 1 mod n. Ka is gonna be congruent with 1, mod n. Yeah, I guess I'm gonna have that Ka is congruent with 1 mod n. And also, so basically K is also in inverse. K is the inverse of A. So I can say from here, I can say that K is equal to A minus 1, which is equal to 1 over A mod n. So it's called the inverse of A mod n, right? And another important detail, it's unique. Is unique. So why it's unique? Is unique because, well, let's suppose that it wasn't unique, right? Then what if there was also some SA, same story, that also went into 1, right? Because, well, if not, because if is unique, if not, then I would basically can pick K different from S, and then I would get what? I would get that Ka is going to be congruent with SA mod n. But now look at this. I know that I can always simplify A on both sides because A and N are good pair, right? So A and N is a good pair. So if I simplify A on both sides, I would get what? I would basically end up getting from here, I would end up getting that K is going to be congruent with S mod N, right? So I would get that from here, the only option is that K needs to be equal S because K and S are numbers from 1 to P to N minus 1, right? So, but we assumed that they're different numbers, right? We assumed that they're unique because if they're not unique, K would need to be different from S. So if they're not unique, I can pick two different numbers, but then I get that K and S is the same number. So basically, contradiction here, right? So contradiction cannot happen, right? Okay, hopefully this is clear. Okay, so the modular inverse always exists, even, for example, even if you don't have a prime number, even if it's like mod n, as long as A and N are a good pair. So for good pairs, the modular inverses always exist, right? Okay, cool. Cool. So now I guess what is the problem with, if I take the numbers, so for example, let's do, I don't know, let's say mod 6, mod 12, mod 15. Let's look at the stuff mod 9, right? So if, for example, I looked at the remainders mod 9. So what are the possible remainders mod 9? Okay, so if I have the possible remainders mod 9, I see that I'm gonna have what? 1, 2, 3, 4, 5, 6, 7, 8. These are the remainders, mod 9. Okay, so what is the modular inverses of each one? Okay, so 8 is minus 1 mod 9. So if I pair minus 1 with minus 1, I still get 1 mod 9. So 8 times 8 gives me 1 mod 9. 1 and 1 gives me 1 mod 9. But what about 2? What's the modular inverse of 2 mod 9? Well, 2 is a good number to 9. So 2 is going to have a modular inverse, right? So 2, I need to multiply it with what? 2 times 8 is minus 1. 2 times 5 gives me 10, right? So 2 times 5 gives me 10, which is congruent with 1. So I can pair actually, 2 and 5. Now, if you look at 3, well, 3 is actually a bad number to 9. So 3 doesn't have a modular inverse. So 3 is bad number to 9. So 3 is not going to have modular inverse. 6 is also a bad number to 9 because 6 and 9 have a common factor 3. So the only thing that's left is 4 and 7. So what's the modular inverse of 4 and what's the modular inverse of 7? If you take 4 times 7, you see that you get 28. You see that we get 28. So 28 is going to be 27 plus 1, which is also going to be congruent with 1 mod 7, right? So I can write it down here. 1 times 1 is congruent with 1 mod 9, and then I can write, 2 times 5 is going to be congruent with 10, which is going to be congruent with 1 mod 9. And then I'm going to write, 4 times 7 is going to be congruent with 28, which is congruent with 1 mod 9. And then I guess, 8 times 8 is going to be congruent with 64, which is going to be congruent with 1 mod 9. Okay, so now I guess what do we see? So we see that mod 9, any other number n, we see that they also go in pairs, right? So 2 goes with 4, 2 with 5, 4 goes with 7. But this is actually, it's not always the case. So for example, let's try and pick another mod. So for example, if we do this mod, let's say mod 10, right? So if I were to look at the numbers mod 10, what would I have mod 10? So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the remainders mod 10. And now which one of them have a modular inverse? So I guess clearly 9 goes with 9, 1 goes with 1. But then if you look at this, you're going to have some bad numbers. So 2, what are the numbers that are bad to 10? 2 is bad, 4 is bad, 6 is bad, 8 is bad, and 5 is bad. They don't have modular inverses. So I guess the only thing that we're left with is going to be 3 and 7 that are going to be, I guess 3 times 7 is 21. So it gives you 1 mod 10, right? So these two go in pairs. Okay, let's look at some other numbers. So for example, maybe not mod 9, but maybe not mod 10, but how about mod, let's see, if we try mod 4. So if we try mod 4, what would we get mod 4, right? So if I look at this, 1, 2, 3, 1, 2, 3, I guess that's too small, but maybe a bigger number. So how about we try mod 15, right? So what if we look at the numbers mod 15? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? So these are basically the remainders mod 15. So we're looking at, as 15 here, we're looking at as 10, we're looking at as 9. So far we see that always the first has its own modular inverse and the last has its own modular inverse, but all the others go in pairs. But then how about if we try, or actually maybe not 15, we could have also tried 12. Yeah, actually, how about we try 12? So let's actually try, let's not try mod 15, let's try mod 12. So if I look at mod 12, right? So what would happen for mod 12? So this would be the remainders mod 12. So this would be as 12. Okay, so then what are the modular inverses of each of this? Well, 1 is clearly paired with 1, 11 is paired with 11. Well, some numbers in here are going to be bad, right? So for example, 2 doesn't have a modular inverse because it's a bad number. 4 is bad, 3 is bad, 6 is bad, 8 is bad, and 9 is bad, and 10 is bad. So actually the only other good numbers is 5 and 7. And now you might think that, hey, you know what? Probably 5 and 7 need to be paired together. But what do you notice? When you multiply 5 times 7, you get 35, and you get that this is congruent with -1. So they're actually not modular inverses of each one. Actually, what's interesting in here is that 5 gets paired with itself because 5 times 5 is 25, which is congruent with 1 mod 12, right? And similarly, 7. 7 times 7 is going to be 49, which is 48 plus 1. So it's also going to be congruent with 1 mod 7. So we see an interesting property. So, if you had a prime number, whenever you have a prime number, they always So let's see. So whenever you have a prime number, it's always the first with the first, the last with the last, and everything else goes in pairs, right? So we see it in here. It's like the first with the first, the last with the last, and then everything else always goes in pairs. And then when we combine this, we get Wilson's theorem. And then all these numbers are going to be good to P, right? But then if we look at, for example, and we see the same thing, for example, mod 11, right? But then if we look at like something that's not a prime, if you look mod 9, mod 10, mod 12, you see that there's going to be some numbers that are bad. So these bad numbers, they're not going to have a modular inverse. So if you want to get a modular inverse, you only need to play with the good numbers, only the good numbers. Yeah, I guess why don't bad numbers have a modular inverse? Why can't I find a modular inverse for like a bad number? Well, here's an idea. Let's say that I had some number a and n that's bad. So let's say that a and n has some common factor d, right? Then let's say that we had some modular inverse. So let's say that I had that ak is going to be congruent with 1 mod d. Sorry, mod n, right? So what would happen if I had a modular inverse? So let's say that AK is congruent with 1 mod n. Then notice one thing right away. Well, n needs to divide their difference, right? So you can always write it like this. N needs to divide their difference, which is AK minus 1. So you can say that AK minus 1 is going to be some n times d, right? But now what is the problem in here? Look, if a and n are a bad number, then this is going to be divisible by d. This is going to be divisible by d, but this one is not divisible by d. So not possible, right? Not possible. So this is not possible. So basically, no such k. No such k. So no inverse for bad numbers. Right? So a and n. So we start in here with it being a bad pair, right? Bad pair. So yeah, if it's a bad pair, you can't really do much about this. It's not gonna have a modular inverse. And we also see that, some of them can go by themselves. Why is that the case? Why can I have this thing going on? Well, because look at this. I don't like, I can have, if I look at all these numbers, it's also possible. So for example, if I had mod n, so mod, I guess, can I have in here, a to be paired with itself? Can I have, for example, a squared to be congruent with 1 mod n? Remember that normally I was allowed to take square root, but in here I cannot do square root anymore. So actually in here it could be multiple solutions. So like one solution is that, for example, so we see that, if I were to look at, what are the solutions, a squared is going to be congruent with 1 mod 12. And we see that there is a couple options for a. So a can be either 1, 11, or I guess 5, or 7, right? So there's actually like multiple numbers that are like solutions. All of this are going to give you 1 mod 12. All right, cool. So I guess we have Wilson's theorem. Okay, so now what can we do? What can we do next with this? I guess we can discuss this better in a bit more detail. Yeah, actually, I guess this is probably like a good, stopping point. So let's do a 1-minute break in here, and then we're gonna continue into the second part of the class. All right. All right, so I guess let's get now into the second part of the class. So let's see, in the first part, what did we do so far? So we discussed Wilson's theorem. By the way, if you wanna, I guess I'll share some links at the end. So now, I guess in the second part, I wanna go and look at Bezout's theorem. So let me write down what Bezout's theorem is. So Bezout is basically saying, so let's write it here. Bezout's theorem. And basically it's saying the following. If you start with a good pair, so if you have some good pair, let's say A and B, that's a good pair, right? Then this is saying the following, that there is going to exist some X and Y such that they satisfy the following property. AX plus BY is going to be equal to, 1 is equal to 1. So the question is, how can we get such X and Y? So basically, you can think about it this way. So let's say that I give you two numbers, for example, 3 and 5. 3 and 5, and what you see is that 3 and 5 are relatively prime. So then the question is, if you look at like different combinations of 3 and 5. So let's say that I take 3x plus 5y, and x and y are allowed to be positive and negative. Then what are all the numbers that I can get in here, right? So I guess one thing that you can notice is the question is, can you get, I guess if I, for example, tried x and y. So if, for example, if I tried 2 and 1, then I see that I'm going to get 6 plus 1, I'm going to get 11, right? But I could, for example, also try 1 and 1, right? Then I see that in this case, I'm going to get 3 plus 5, I'm going to get 8, right? Where I could, for example, try, 0 and 1, and I see that I'm going to get 3. Where I can try, 0 and 1, and I see that I'm going to get 5, right? Or I guess what are like some other numbers that I can try? So you can think about this, can I try some numbers x and y that, what are like all the possible values that I can get in here? And for example, the most interesting value you're interested in is, question is, can you get 1? Because, well, what is the big deal with 1? Because let's suppose that I was able to get 1. Then one thing I can do is I can come and I can multiply this by d, multiply this by d, and I multiply this by d. And what do you see? You see that, then I can get, or I guess not d, but let's say n, right? So if I come and I multiply this by n, I multiply this by n, and I multiply this by n. And if I were to do 3 times xn, 5 plus yn, I see that I can get any number n, right? So if I could get 1, just multiply everything by n, and you can get any number n from 3s and 5s. So I guess, yeah, the question is, what other numbers can I get? And can I get 1? Because 1 is the most special one. And turns out, in this case, if you think carefully, you see that, for example, if you use, 2 and, for example, minus 1, then what are you going to get in here? You're going to get 6 minus 5, and then you're going to get 1, right? Which is cool. So basically, we know that 3 times 2 plus 5 times, minus 1 is equal to 1. So I can come and I can multiply this by, n, by n, and I'm going to get n, right? So basically, what this is saying is 3 times, 2n plus 5 times, minus n is going to give me n. So, yeah, so basically, I can get any number n from 3s and 5s. So the theorem says that, as long as A and B are good to each other, or 3 and 5 are good to each other, I can always find x and y that give me, 1. So when I combine them with AB, right? So I can always find some multiple of A with some multiple of B to give me 1. So let's kind of like try and prove it. So let me write this again. So let's say that, A and B are a good pair. So let me use the right thickness. So let's say that, A and B is a good pair. And the question is, so the theorem says that I can find x and y such that ax plus, by is equal to 1. Well, what does this mean? Well, there's two properties in here that you can say. The first thing is that you either get that, by is going to be equal to ax minus 1, or you can write it as ax is going to be equal to by minus 1, right? So I guess from here you get that, either b is going to divide this or a is going to divide this. So now, well, I guess if you look at the first line mod b, right? What does the first line mod b say? So basically it's saying that ax minus 1 is a multiple of b, right? So ax and 1 have the same remainder mod b. So basically, I guess what I'm trying to say is that, ax minus 1 equal to by, it means that, ax is going to be congruent with 1 mod b. Or you're going to have that by is going to be congruent with 1 mod a. So basically, the theorem is saying, how can I find such x and y? Well, the way you can do it is you can find an x that's a modular inverse of A mod B, right? So if A and B are a good pair, then, I can pick x to be the modular inverse of A. So basically, pick x to be inverse, to be equal to A minus 1, which is, 1 over A. So basically x to be inverse of A mod B. Well, then what do I have from here? Well, then from here, I'm going to have that, AX is going to be congruent with 1 mod B. So it means what? It means that AX minus 1 is going to be congruent with 0 mod B. So it means that, AX minus 1 is going to be some multiple of B, right? There's going to be some B times some number T. So I can, move things from one side to another. So I'll get that AX minus BT, right? Or I can write it as plus B times minus T is equal to 1, right? And then I'm just going to make this to be my Y. So I'm going to have AX plus BY is equal to 1. All right. Okay. So hopefully this is clear. So basically, Bezout's theorem, it's saying that, hey, the only, like, if I wanted to show that X and Y, such X and Y exist, well, how can I do it? Well, I just need this equation to be satisfied, or this equation. You just pick one, whichever you want. Like, either one gives you the same result. So for example, if you pick this equation and you say, okay, AX is going to be congruent with 1 mod B, then I'm just going to pick X to be a modular inverse of A. And I know that such an X exists mod B. Why? Well, because think about, well, how do we show that, A has an inverse mod B? You start with the set as B, right? Which is going to be this remainders 1, 2, 3, all the way until, B minus 1. And you look at the set A as B, right? This is what we always do. We take a set and we multiply it by A. So we're going to have A, 2A, 3A, all the way until, B minus 1, A. And as long as A and B, so we're looking at stuff mod B here. So as long as, A and B are a good pair, so A and B are a good pair, there is going to be some number in here, right? There is going to be some number, I don't know, like some KA or some XA that's going to go into 1 because these two sets are the same sets, right? So there's going to, I don't know what the X is. So the theorem, Bezout's theorem, doesn't tell me what X is going to be, but it just tells me that such an X exists and such a Y exists. And how do I show it? Well, there's going to be some number here that goes into 1. So pick that X, right? Pick X to be this thing that goes into 1. So I'm going to have, AX is congruent with 1 mod B, move it to the other side, AX is congruent with 0 mod B. So it needs to be a multiple of B, right? So it needs to be some B times T, right? And then move it to the other side. And you get this equation, AX plus B times minus T is 1. So basically what this means is that, hey, you take A times something, B times something, and you get 1. So that's it. That's Bezout's theorem. Bezout's theorem. So let's actually, I'm going to write it here. Right, so this is, yeah, so basically this is the proof of Bezout's theorem. All right, cool. So now I guess there is a question, okay, about Bezout's theorem. Well, what if A and B are not good to each other? What if, A and B are bad numbers? What can we do with bad numbers? Can we still find X and Y that are going to give me some number? Well, in here you guys see, so like, if I had X and Y that gave me 1, then I can always come and multiply this, X and Y by some number N. So I multiply this by N, and I'm going to get N, right? So basically, if A and B are good to each other, I can always find some X times N, Y times N, such that when I pair them, basically, I can always find some multiple of A plus some multiple of B to get any number N, right? So then the question is, well, what if A and B are not good to each other? Can I still get any number? And in particular, can I get 1, which is the smallest number? Well, and we can look at this in more details, right? So, let's say that A and B are bad, right? So if A and B have some common factor D, so then the question is, can I find, X comma Y such that, AX plus BY equals 1? And turns out that the answer is no. So, well, let's see what can we do? So basically the answer is going to be no, but what can we do instead? And why is this a problem? Well, look at this. The reason is if it was possible, then this would be a multiple of D. this would be a multiple of D, but this one is not a multiple of D. So basically, there is no way you can find some multiple of D plus another multiple of D and get something that's not a multiple of D. If this both are multiples of D, this also has to be a multiple of D. Or like more generally, I guess what I'm trying to say, so what can we do instead? So whenever you have a bad pair, you can always make it a good pair, right? So how can we get, a good pair from a bad pair? Well, you can write that, A is going to be equal to, let's actually keep using red. So I'm going to have that A is going to be, in this case, A is going to be equal to some A0D, and B is going to be equal to some B0D. So I guess if I were to have this equation, what would this equation become? This equation would become A0dx plus, B0dy is equal to 1. So if you look at this is the problem. I cannot have D times A0x plus, B0y is equal to 1. Because look, this is a multiple of D, but this one is not a multiple of D, right? So there is, no solution to this equation. So no solution. So what can I do instead? Well, I guess if I got like some good, so basically I can always start with a bad pair and I can make it a good pair, right? And what's going to be the good pair in here? So I guess one thing you can look at is, look, if A and B are bad, right? And I take the bad stuff out, D, then I'm going to get A0 and B0 to be good, right? So basically I'm going to have that A0 and B0 now are going to be a good pair, right? So now if they're a good pair, I can look at the previous theorem. I know that if I start with a good pair, I can combine them to get one. So if these two are good, so basically, it's good pair. So good pair. This one here was, bad pair, right? So bad pair. Okay, so if I have a good pair, I can always, apply, Bezout's theorem for the good pair. So I can find, so there's gonna exist, some x and y such that the following satisfied ax. So basically a0x plus, b0y is equal to 1. And now what is the next thing I can do? Well, I can come and so if this happens, I can come and I can put back D. So basically, if I put D in here, I put D in here, and I put D in here, then what am I gonna get? So if you look at A0D, well, what is A0D? A0D is just A. So I'm just gonna get what? I'm gonna get that AX plus, so basically what I'm trying to say is that this thing is A and this thing is B, right? So basically the final result that I can get from here is the following, that, I'm going to have AX plus BY is equal D. So yeah, this is the more general Bezout theorem. If A and B are bad, then one thing you can do is you can get D, right? So basically, this cannot happen. This would need to be, like, the only way you can do it is if you make this a D, right? Because you can make this to be 1. So I can make, this thing in here to be 1, but it's still going to be D times 1. So this thing, like the least number it can be D, right? So this number can the least be a D. So now actually, let's see. So this is the smallest thing you can get. So basically now let's say that I had some, so actually if I come and I multiply this by any number k, so if I multiply this by any number k and I multiply this by any number k and any number k, I see that A times something plus B times something, it's always gonna be, dk. So basically, if I take A, combine it with something, and take B, combine it with something, I'm always going to have to get a multiple of D. I cannot get something that's not a multiple of D, right? Exactly because of this reason. Look, this needs to be a multiple of D. This is a multiple of D. It means that this one needs to be a multiple of this. So this needs to be some, dk, D times K. K, and the very smallest thing it can be is D, right? D is the smallest number that's a multiple of D. So yeah, so this is basically the general Bezout's theorem. So Bezout's theorem says that, if they're relatively prime, you can combine them to get a 1, but if not, you can combine them to get, the thing that makes them bad, the greatest common divisor D, which I can eventually, take out from everywhere and get back the original equation. Okay, so this is actually kind of like cool, because this tells us how to find the modular inverse when, a number is bad. So if you look at what we discussed previously, where we said that, look, if A and N is bad, then basically A, like, there is no such case, no inverse for bad numbers, right? So we said in here that if A was a bad number, it wouldn't have any modular inverse, mod N. But what is the closest thing that we can find to a modular inverse? Turns out we can still, do something in here. So I guess what could we do? What is the closest thing to a modular inverse when the number is bad? Well, you can start with Bezout's theorem, right? So Bezout's theorem basically tells us that, well, if A and N is bad. By the way, notice one thing, Bezout's theorem. So basically, if Bezout's theorem is true, then it means that modular inverse exists. And if modular inverse exists, Bezout's theorem is true. So you can go either way, right? So you can, if you know about modular inverses, you can prove Bezout's. Or if you prove Bezout some other way, I'm going to share some links with you, then from Bezout, you can get like right away that the modular inverse exists. I think our proof is better because it's easier to see, as long as you know that these two sets are the same, it's always easy to see that, there has to be a modular inverse. And then from there to prove Bezout. If you try to go the other way, it's slightly longer. Okay, so now let's say that, A and N are a bad pair. So they have some common factor D, so they're, bad pair. So bad pair. So what can we do with, this bad pair? So ideally, I would want to find some AX that's going to be congruent with one mod N. So I would want to find something that's a modular inverse. But then what is the problem with this? Well, the problem with this is that I would have that, AX minus 1 is going to be congruent with 0 mod N, right? So this would mean that AX minus 1 is going to be, basically some N times D, right? And then the problem is that what? That this is a multiple of D, this is a multiple of D. So actually what this means is that this one also needs to be a multiple of D, but it's not, right? So this is a contradiction. There is no modular inverse for A. Okay, but what is the closest thing? What is the smallest value that I can get in here that still, like makes this equation work? And that's basically, it comes from Bezout's theorem, right? Because Bezout's theorem tells me that I can find X and Y. From here, it means that I can find some X and Y to combine them to get AX plus, NY is equal to, this D, that's, the common bad thing. And from here, I guess, what can I do? I can move N on one side, D on another side. So if I were to look at this, mod N, so basically I would get that what? NY minus NY is equal to AX minus D, right? So basically, from here, I get that, AX is going to be congruent with D mod N, right? So basically, I cannot get a modular inverse mod N. I cannot make this one, but at least I can make this thing to be D, right? And then how can I simplify this? Well, one way to simplify this is, I guess, if you think about any bad numbers, right? You can always make them into like a good pair. How? You can write A is going to be equal to some A0D, and N is going to be equal to some N0D. And now look at this. A0 and then N0 are going to be a good pair. So this one is going to have a modular inverse, right? So if these are good pairs, I can find some, for A0, I can find some number K such that this is congruent with 1 mod N0. So now if I come and if I multiply this by D on both sides, so if I multiply this by D here and I multiply this by D here, then what am I going to get? Well, this thing here is just going to be A. So I'm going to get, AK is going to be congruent with D mod. And I can also multiply this by D, right? So mod N, right? Why is that the case? Because look at this. If you look at this thing and you try to simplify it, you'd get, A0 dx is going to be congruent with D mod N0D. So now, normally, what I would want to do is I would want to come in here and simplify D on both sides. But what do I see? I see that, X and N are bad, or like D and N are bad, right? D and N, they have common factor D. So basically, when I simplify the D, because this one also has a D, this thing that I'm trying to simplify is bad because it's containing here. I need to cancel it from here as well, right? So basically, the equation that I end up getting in here, is this equation. A0x is going to be congruent with 1 mod N0, which is exactly the same equation that we had in here, right? There is going to be some A0 times K that gives me 1 mod N0. So basically, I guess what I'm trying to say in here is that, if the numbers are bad, you can make them good, and they're going to have a modular inverse. So A0 is going to have a modular inverse N0. And now what you can do is you can add the bad stuff back. But then the effect of that is going to be that, when you take A and you multiply it by the original modular inverse, you're gonna get that you're not gonna get 1, but you're gonna get D mod N, right? So basically you cannot have a modular inverse mod N, but you can have something that's very close to it. This number, K, which is gonna, when you're gonna pair them, you're gonna get D, which is the thing that makes them bad. Yeah, this is only for when A and N are bad. Clearly, if A and N are good, this is possible, right? If A and N was, a good pair, so this would be fine, right? All right, cool. So yeah, so this is kind of like the main idea about, modular inverses and Bezout's theorem. And let's see if there's anything else we should discuss. Yeah, I do have a couple more ideas. So maybe, let me share a couple links that I think are, relevant for what we've been discussing in here. So if you guys want to learn more about, Bezout's theorem, modular inverses, and such and such and such, I definitely recommend looking at Brilliant and, reading their theorems. They're a great resource. I'm going to put Wilson's theorem in the chat. So I guess you can read about Wilson's theorem, which says that, basically P minus 1 is going to be congruent with minus 1 mod P. And, this property only happens for primes. If you have some other number n that satisfies this, the only way they can satisfy this is if n is a prime, right? How can you show that n is a prime in here? Well, you can look at like this theorem. What does it say? N minus 1 factorial is going to be congruent with minus 1, which is congruent with n minus 1. So now you can cancel an n minus 1 on both sides. So you're going to get, 1 times 2 times 3 times, n minus 2 is going to be congruent with 1 mod n. Basically, what I'm trying to say is that actually, don't even need that. If you look at like this thing, well, this thing is just going to be congruent with 1 times 2 times 3 all the way until n minus 1. And now look, if n was some not a prime, but some composite number a b, then there would be somewhere here an a and somewhere here would be a b. So then this entire thing would be congruent with 0 mod n. But we have that it's also congruent with minus 1, but it's also congruent with minus 1, and it's congruent with n minus 1. So how can, n minus 1 be 0 more than? Well, the only option, this cannot happen, right? This is contradiction. So this cannot happen. It means that not composite. So not composite. So it means that n is prime. So this is also like another way to check that a number is prime, is you check Wilson's theorem. You look at n minus 1 factorial and you see that it's minus 1. But this is a very slow method because computing this number, it's going to be a very big number. So if you use a computer, computing it is going to be very slow, right? So probably don't want to use that. But yeah, Wilson's theorem basically only holds for prime numbers. Yeah, so now you can look at, for example, different values of n, 2, 3, all the way until here, and look at n minus 1. And then check what is it mod n. And then you see that mod n, you get a bunch of zeros. So these are not primes. But those that are not zeros, you see that they're going to be congruent. Actually, 6 is minus 1, 4 is minus 1, 2 is two is a problem, right? But everything else is also minus 1. So you see that only the numbers that give you minus 1 in here, or the numbers that give you n minus 1 mod n, only those are going to be prime. But yeah, this is a very slow. Like if you want to check 2, 3, or 5 or prime, or like bigger numbers, it's much easier to, just look at, like, there's other methods to check if this number is prime in comparison with computing the factorial, because the factorial is you have to compute a big number and then it's too much work. Yeah, so like let's say that now, we are interested in this property in here. So compute 30 mod 899, right? So I guess if you look at 899, you see that it's made out of 29 and 31, right? So 29 and 31. And I guess here's an interesting property. So maybe I should discuss this in a separate page. Let's say that I had some number a. So let's say that a was congruent with b mod n, which was equal to, I don't know, it's like two numbers ts. Maybe n is a composite number ts. Right? Then what can we do with actually let me rewrite it the other way. So let's say that I had two numbers, t is going to be congruent with s mod n, which is composite, which is made out of two numbers a and b. Well, then what can we do in this? Well, what this means is that t and s have the same remainder mod n, so it means that n needs to divide the difference, a t minus s, right? T minus s, but n is equal to ab. So it means that, from here, I'm going to get that, a is going to divide t minus s and b is going to divide t minus s. So it means that, t is going to be congruent with s mod a. So basically, t is going to be congruent with s mod a. And you also get that t is going to be congruent with s mod b. So basically, one thing that you can do is you can split this into two, right? So you can write the same equation mod A and the same equation mod B. So if t is congruent with S some product, then t is going to be congruent with S mod A and with S mod B, right? And you can also go the other way. If t is congruent with s mod a, it can also go the other way. You can also say that, from here you're gonna get this, and you're gonna get this, right? If you have this, you get this. If you have this, you get this. But now if you have this, from here, you see that if you combine them, you're gonna get that AB divides t minus s, and then from here, you see that you can get this. So basically, you can also go the other way. So, yeah. So I guess how is this helpful? Because if you look at like our example in here, right? You're interested in like what is this 30? What is 30 congruent to mod 899? Well, one thing you can do is you can start with small numbers. So you can see that this is gonna be 29 times 31. And you can see that they're both prime. So I can actually ask an easier question. What is 30, congruent to mod 31? And by Wilson's theorem, you see that, this is P, this is going to be P minus 1, and it's going to be congruent with minus 1, right? Mod 31, which is going to be congruent with 30. Okay, cool. So 30 factorial is going to be congruent with 30. And now what about 30 factorial mod 29? So if I look at mod 29, I see that 30 factorial is going to be congruent with well, it's going to be congruent with, 0, right? Mod 29, because, it's a multiple of, it already contains a 29 inside. Okay, so I guess what can we do with this? I guess, yeah, there is this thing, which is basically the Chinese remainder theorem that basically tells you how to combine the two of them to get, what is 30 factorial congruent to mod this. Yeah, we'll take a look at that maybe in the future. But to give you guys an idea, here is how we could solve this system. So, think about this, this being some number a. So this is your number a, and this is your number a. Then one thing you can say is you can start with sort of like the biggest one. So you can say that, from here, you can say that, a is going to be equal to 31k plus 30, right? And then you can take this thing, and you can plug it in here, and you can get that 31k plus 30 is gonna be equal to, I guess, is gonna be congruent with 0. It's congruent with 0 mod 29, but it's also congruent to, well, so what is this congruent to mod 29? Well, 31k mod 29 is gonna be congruent with 2k, and then 30, what about 30? Is congruent with 1, right? And this entire thing, so this is your a. And I know that a is also congruent with 0. So I can write this is congruent with 0 mod 29. So basically, what do I need? I have the following thing. 2k is going to be congruent with minus 1 mod 29. And now look, 2 and 29 are good to each other. So I can multiply by 2 inverse on both sides. So I would get, I guess, I would get 2 and 2 inverse would cancel. So I get k is going to be congruent with minus 1 times 2 inverse mod 29. And yeah, if we knew the modular inverse, we could figure it out very easily. All right, cool. So hopefully that is clear. So you can guys read more about Wilson's theorem in here. There is, a proof of Wilson's theorem. The proof in here uses, I think, polynomials. It's like much more advanced. We don't really need this proof. But here's a couple like simple applications, right? So for example, show that this number divides 18 factorial plus 1. And well, what do you see? You see that 437 is 19 times 23. You can check the 19 is a divisor and this one's a divisor. Well, why is that the case? Because, 18 factorial is going to be congruent with minus 1 mod 19. So I guess if I move it on the other side, I'm going to get 18 factorial plus 1 is going to be congruent with 0 mod 19, right? So I guess, yeah, 19 is a divisor. But how about 23? Why is 23 a divisor in here? Well, that one is a bit more tricky, but we can figure it out, right? So now we're left to show that also 23 divides, 18 factorial plus 1. So we need to find 18 factorial, I guess, mod 23, right? And if we use Wilson's theorem, we know that 22 factorial is going to be congruent with 22, and is going to be congruent with minus 1 mod 23. So I guess if I cancel 22 on both sides, I can write 21 factorial is going to be congruent with, I guess, 1 mod 23. So if I look at, well, what is this? This is also congruent with 18 factorial times 19 times, 20, right? Times 21. And then if you look at this thing, what are this mod 23? Well, 21 is going to be congruent with minus 2. 20 is going to be congruent with minus 3. And 19 is going to be congruent with, I guess, minus 4, right? So this entire thing is going to be congruent with, 18 factorial times, well, what is this? minus 24, right? Minus 24, which is, what is minus 24 mod 20? Well, so I guess what do I have in here? So this is going to be, so this is also, so this, all of this is going to be congruent with 18 factorial times, you know, minus 1 factorial mod. And the final result is, I know that this entire thing is congruent with 1, right? And it's congruent with 1 mod 23. So what does this tell me about 18 factorial? Well, what should be 18 factorial? So if I come and I multiply by another minus 1 in here, I multiply by another minus 1 and by another minus 1, I get that, you know, this two would cancel. So I get that 18 factorial is going to be congruent with 1. So 18 factorial is also congruent with, you know, minus 1 mod 23, right? All right, cool. So basically it means 23 divides, you know, 18 minus 18 plus 1, 18 factorial plus 1. Okay, so yeah, so that's it. Yeah, that's how Wilson's theorem is really, really helpful in here. You get that 18 factorial is minus 1. But also, you know, if you look at it mod 23, you also get that 18 is congruent with minus 1. So yeah. Yeah, this is exactly the trick. Is if you multiply it by 20. So if you look at basically, you know, Wilson's theorem, which is 22 factorial, which is congruent with minus 1, which is congruent with minus 24. But if you look at like minus 22 factorial, it's going to be 22, 21, 20, 19, 18. And if you look at like all these numbers, they're going to be minus 4, minus 3, minus 2, minus 1. And then when you put them together, you get 24 in here, right? So if you cancel 24 with 24 on both sides, because they're good to 23, you get 18. It's going to be left minus 1. Yeah, so that's basically the way it works. There's a couple more problems here using Wilson's theorem. So I encourage you guys to, you know, work through this document and try to solve it. So that's the part on Wilson's theorem. But then we also have a part on Bezout's theorem, right? So Bezout's theorem is basically saying this, that, you know, if A and B are good to each other, then you can find X and Y to get 1. But if they're bad, they have some common factor D, then you can find X and Y to make D, right? Yeah, so this is, yeah, I guess this is Wilson's theorem. This theorem actually tells you how to compute X and Y. So if you actually read through the Euclidean algorithm, you can see how to compute X and Y. The idea is basically the following. So let's say that, you know, I had A is 102, B is 38. Then the question is, you know, what A and B should I use to, what X and Y should I use to get 1, right? So basically, you know, I want to find some number times, you know, 2. And so yeah, so I guess if I look at like these two numbers, what do I see? So I want to find some AX. So basically in this case, it's going to be 102 times some X plus, you know, B times Y, right? So time plus 38 times Y, and I want to get the common factor D. Well, what is going to be the common factor? D is going to be equal to 2, right? That's what, 102. If you look at 102 and 38, which is the common factor of A and B, this is going to be 2. So basically, you know, the question is, can I find some X and Y to pair them together to get 2? And how could I do that? And basically, it's using the Euclidean division algorithm. So you look at 100. So the way you started is you started with the biggest number that you have, right? So this is the way you do it. So you take 102 and you look at 100. So you start with, I guess your numbers A and B are going to be, you know, 102 and 38, right? So you start with 102 and you write it like this. Okay, so now I guess, you know, you take 102 divided by 38. So you get 2 times 38 plus 26. And now you look at 38 and you try to decompose 38 into 26s. And then when you decompose 38 into 26s, you get this thing in here, that is 1 plus 26 plus 12. And now you take 26 and you try to decompose it into 12s. And you get that 26 is going to be 2 times 12 plus 2. And now you take 2 and you try to decompose it into 12 and you try to decompose into 2s, and you get that 12 is going to be 6 times 2 plus 0. And then you stop here. So now how do you go the other way? Well, to go the other way is basically, now that you've got this common factor D, this is one thing that you're going to do. So if you look at this common factor D, this is going to be your common factor D. Well, you can write that this thing in here, it's going to be equal to the difference. It's going to be equal to the difference between these two. So it's going to be this minus this, right? And now, I guess, what about 12? Well, 12, again, you can write it. You can say that 12 is going to be, so actually, let me use red everywhere. So So I guess this is how you go the other way. So you say that now you write this is equal and you put a minus here. You write this is equal and you put a minus here. You write this is equal and you put a minus here. And now what are we gonna do? So we're gonna do, well, we're gonna take this number in here and replace it for 26. So actually, I guess no, the other way. So I guess yeah, so if I look at like this two in here, it's gonna be the difference, right? So now if you look at this number, so I guess the next thing is what you're gonna do is you can take this thing in here and you can plug it into 12 because you know this is your 12. And now for the same thing for 26, if I want to plug 26, I can take this thing and plug it into here. So basically, I take this thing and I plug it into 26. I take this thing and I plug it into 12. And then I look at like this and also into like this 26 in here, right? Yeah, and then eventually I'm gonna get that like it's a combination of 102 and 38. So right, so basically if I wanted to get 2, it's gonna be this difference. And look, here I have two unknowns. I have the 26 and the 12. And 12 and 26, I both computed them. So 12, I use the formula for 12 that's using, you know, stuff with 36s in it. So yeah, and then the 26, I also replace it with, you know, this formula in here. So eventually, when I simplify everything, I get that everything is going to be made out of terms that contain 102 and 38. All right, so hopefully this example is clear how to get x and y. It's kind of like a long process, but if you have the time, you can certainly do it. What we did in the first part of the class is we just proved that, you know, such an x and y, they always have to exist. We didn't really explain how to get those x and y's. So for example, here is another example. Look at these two numbers, 2014 and 4021. You can actually see that these two are good pairs. So because they're good pairs, there's going to be some x and y that give me 1 in here, right? So how do we find such x and y? Well, I guess here's the solution, but this solution is kind of like hard to guess. So how can we see it? Well, you take 4021 and divide it by 2014, right? So when you divide 4021 by 2014, you get a remainder 2007. And now you take 2014 and divide it by 2007, and you get a remainder of 7, right? So now what you do next is you take 2007 divided by 7, and you're going to get a remainder 5, right? You get a remainder 5 here. And then you take 7 and you divide it by 5, and then you get a remainder 2, and then take 5 divided by 2, and then you get a remainder 1. So now look at this thing in here. So what do I have? So I guess I can go the other way. So I can, you know, say that this is equal, 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 and then put a big minus, 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 minus. And now what am I gonna do? So the one thing I'm gonna do is I'm gonna take this 2 in here. So I'm gonna take, you know, all of this. This is equal to 2. So I'm gonna replace this in here. So it goes here. So it's gonna go in place of this 2. But now I still have the 7s and the 5s. So I can do the same story with all of this. It's gonna become a 5, but then the 5 goes in here. And then I guess all of this is gonna become a 7, but 7 is gonna go in here. And now all of this is gonna become a 2007, but 2007 is gonna go in here. So basically take this, put it in 2007, put it in here, so basically, yeah, so you can go all the way back. And then basically the remaining ingredients are going to be left is you're going to have that 1. Oh, and also I have like, I have a 5 in here. So I would, when I replace the 7, I actually need to plug a 7 in here. And I need to plug the 7 in here as well. So this 5 also is going to go into places here and here. And this 2007 is also going to go into places in here and in here. Yeah, so basically you get, by using this method of like back substitution, the only terms that, you know, don't get, like everything is going to become in terms of 4021 and 2014, because, you know, you get 1 here is equal to this, and now you take 2, you plug this into 2, and then you look at this formula, and then you take 5, and then you plug 5 in here and in here, this formula for 5, and then you take this formula for 7, and you plug it in here and in here, and take this formula for 2007, and then you plug it in here and in here. All right, cool. So yeah, so that's basically, you know, how you use Bezout's theorem. And then when you try to do all this computation, you're going to get your x and y to be this, you know, crazy numbers, 863 minus 1723. Yeah, so this is the idea on Bezout's theorem. Now the proof of, so basically, yeah, if you know that, Bezout's theorem holds, then you can get modular inverses, right? Because, if A and N are good, so if A and N are a good pair, so good pair, right? Then basically there is going to be some X and Y such that AX plus NY is going to be equal to 1. So now if you do this, if you look at this mod n, so if you write this mod n, you're going to get that AX is going to be congruent with 1 mod n. Yeah, so basically what this means is that, if Bezout holds, then it means that A is going to have a modular inverse mod n. Yeah, but it also goes the other way. So we use it the other way. We say that we know modular inverses exist and we prove Bezouts. What they do in here is they say opposite. They say that, oh, if Bezouts hold, then modular inverses need to exist. All right, cool. And now the proof of Bezout's theorem, well, it's actually basically using the same, Euclidean division algorithm that we have in here. So, if I had A and B, so let's say that, A is greater than B, then you divide A by B, so you're going to get some remainder, R1, and then you divide B by the remainder R1, you're going to get another remainder R2, and you keep going like that. And then eventually, you keep simplifying it until you don't have any remainder. So what's happening when you don't have any remainder? Now you rewrite this. So you change the signs, right? To say minus, 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 minus everywhere. And this is equal, equal, equal. And then what do? You take this formula. So you take basically this formula, you plug it in here, which is gonna go in here. And then you take this formula, you plug it into Rn, which is gonna go into here and into here. And then you can keep going like that. And then eventually you're gonna take this formula, plug it into R1, and then take R1, plug it in here and in here. And then you're gonna take this formula here for R2, and then you're gonna plug it into here and into like another R2, and you can keep going all the way down. And eventually you're gonna get, your equation that's made out of A and B, and A and B is gonna A with some combination, B with some combination is gonna give you the common remainder D. Actually, if you look in here, this one, A, so if A comma B was equal to some divisor D, then basically the divisor D is gonna be the one that's in here. This is gonna be our divisor D. Okay, cool. Because, well, see, because if A and B, so let's say that A and B had some common divisor D, then, well, this is a multiple of D, this is a multiple of D, so this needs to be a multiple of D. So now this is a multiple of D, this is a multiple of D, so this needs to be a multiple of D. So you can keep going with that. So this is a multiple of D, this is a multiple of D, so this needs to be a multiple of D. But now this is a multiple of D, so now this needs to be a multiple of D. Well, actually, yeah, this one we don't care about this one, but what we get is that yeah, we're gonna get, a multiple of D times this number. All right, cool. So yeah, so this is basically another way to prove Bezout's theorem, but like much longer proof than the one that we discussed originally. All right, cool. So I guess this is kind of like the main idea on Bezout's theorem and Wilson's theorem. So for the last part of the class, I want to discuss modular inverses. So I guess let's do another, 1 or 2 minute break, and then we'll get back for the final part of the class where we look at the modular inverses. And let me just put the whiteboard in here so you guys have it. And yeah. All right, so now I guess let's get into the final part of the class and let's discuss modular inverses and go a little bit into more detail, like what they are and how they work. Okay, so basically the idea is sort of the following. Let's say that, we had a system of like congruences. So maybe I have something like, 3x is gonna be congruent with 7 mod, I don't know, let's say mod 11, right? So here's the thing. So now the question is, so actually let's maybe make it more complex. So let's say 3x plus 5 is going to be congruent with 7 mod 11. So now we want to figure out, okay, what x should I use in order to get 7? When I multiply by 3 and I add 5, I get 7 mod 11. So maybe this could be a problem where you have, let's say that you have 3k plus 5 cookies. So maybe somebody tells you, hey, you have, when you have some number of cookies, and when you try to put it in 3 bags, you have 5 left. But when you try to split it to like 11 students, you get 7 left, right? So if you try to, so you have some number n. So maybe the problem is like this: you have some number n, and I don't know, like somebody tells you that, n is going to be equal to 7k plus 11. Sorry, n is going to be, so basically, let's say you have some number, n is going to be 11k plus 7, but n is also going to be, 3x plus 5. Okay, so this is a totally valid statement. So somebody comes to you and they tell you, hey, I have, some number of cookies, and when I put them in 11 bags, I have 7 left. When I put them in 3 bags, I have 5 left, right? So then the question is, what is this number n, or what is the smallest number n that satisfies this? Or like, tell me at least one number that satisfies this. Well, and now clearly this is, like a way harder problem. But one thing you can do is, well, in order for this to be satisfied, this means that n needs to be congruent with 7 mod 11. So you always start with the biggest mod. So you can look at, mod 11 and mod 3, because these are the multiples. So you start with the biggest one and you write it like this: n is going to be congruent with 7 mod 11. And then the next thing you do is you say, okay, I'm going to take this thing and I'm going to plug it into here. So I'm going to get 3x plus 5 is going to be congruent with 7 mod 11, for example. And now you're trying to solve this system of equations. How can you solve it? Well, clearly move 5 on the other side. So you're going to get, for example, 3x is going to be congruent with, 2 mod 11. So now the question is, how can we solve this? Well, we see that 3 and 11 are good to each other. So I can, for example, multiply by 3 inverse on both sides. So if I multiply by 3 inverse on both sides, basically this 2 would cancel. So I just get that x is going to be congruent with 2 times 3 inverse, which is going to be congruent with 2/3 mod 11. So in some sense, what happened is we had, 3x was congruent with 2 mod 11. So what I did is I just came and I just divided everything by 3, and then just the 3 just disappeared, right? So now you might say that, like, hey, this looks like it's something illegal. You can't really divide by the 3, but I'm not dividing by the 3. When I say that I divide by the 3, I mean I multiply by 3 inverse. 3 inverse is a number, is the inverse of 3 mod 11. Well, actually, we can try and guess what that would be. So if you look at like mod 11, what would be the inverse of 3 mod 11? So actually, I think we already did that at the beginning of the class. When we looked at mod 11, we saw that the inverse of 3 is 4, right? So when I say 3 inverse is actually 4. So like 1/3, this is actually 4. So when in here, mod 11, right? So these are like, the same thing. So for example, when I come in here and I write that, like, I move 3 on the other side, what I mean by here, x is going to be congruent with 2/3. What I mean to say is that it's actually 2 times 1/3. What this means is like it's 2 times 3 inverse. What this means is that it's 2 times 4. So basically this number and this number and this number here is always 4, 4, 4. So basically it's 2 times 4. Sorry, no, it's yeah, so it's always 2 times 4, because 4 is the inverse of 3, right? So I get that x is going to be congruent with 8 mod 11. Yeah, so that's basically the way this equation works. So this is usually the way that you're trying to solve equations. And more generally, you can have an equation that looks like this. Let's say that ax plus b is going to be congruent with c mod some number n, and you're trying to solve this. Well, so how can you do it? Well, you move it on the other side, so you get ax is going to be congruent with b, I guess, with c minus b. So it's going to be congruent to c minus b, which is going to be equal to some number d mod n. So you can write it like this. So you're basically going to write that ax is going to be congruent with d mod n. So what you can do is you can multiply by A inverse or move A on the other side, right? So how do I move it? I multiply by A inverse. So then basically this cancels. So you get that, you know, from here, you're going to get that X is going to be congruent with D divided by A, which is, you know, D times A inverse mod N. So which is basically D times K mod N. Where K is what? K is the inverse of A mod N. Now, in order for this K to exist, we need one more thing. We need, in order to have like the inverse of A, we need A and N to be good, right? So A and N need to be a good pair. So good pair. So check that they're a good pair first. So after we check that they're a good pair, yeah, you can basically, you know, do this thing. All right, cool. So yeah, so this is basically the idea with the modular inverses. And now I guess let's look at a couple practice problems with modular inverses. So I'm gonna share some links in here. So if you guys want to learn more, definitely can read through this document here on modular inverses. So for example, you know, yeah, actually we'll skip this quadratic equation, but we will look at, yeah, let's look at this document in here. So I guess this document, again, it's a really good document on modular arithmetic. I'm gonna put it in the chat, or like reach out to me if you need the PDF. So what do we have in here? So I guess there is like some definition of modular arithmetic, right? So, you know, if A and B have the same remainder, we write them like this, and N divides this. So for example, mod 11, these two have the same remainder. And the remainder can also be, for example, negative, right? Like it means that, well, as long as this minus this, so like, you know, both of them in this case are going to have remainder 10. So 10 is also minus 1. So this idea with the remainders, like what do we see in here? Well, we see that all the numbers, so for example, we look at all the numbers that give me remainder 2 mod 5. So for example, 2, and then I can add plus, so any number of the form 5k plus 2, right? So I can add plus 5, plus 5, plus 5, or minus 5, minus 5, minus 5. All of them are going to have remainder 2. Or like if I take 4 plus 5 plus 5 plus 5, or minus 5 minus 5 minus 5, all of them are going to have remainder 4 mod 5, right? And basically, we see that if we look at, for example, mod 3, the numbers split into 3 groups. Those that give you remainder 3, so of the form 3k. These are numbers of the form 3k plus 1. These are numbers of the form 3k plus 2. Yeah, so now I guess we saw the basic properties of modular arithmetic. You know, if A has remainder R, B has remainder S, then you can add them. So A plus B is going to give you remainder R plus S. Or you can take the difference, or you can multiply them, right? So also their product is true. So AB is also going to give you remainder RS. Okay, so we know that. There's a couple of practice problems. I definitely recommend working through this practice problems in your free time. And now that we get into a couple more advanced problems, I guess we have the special set S, right, that we discussed. So if we have like the set of like remainders, and now we can create the set AS. So this is the set AS of like the remainders multiplied by S. Then I guess let's see, what do we get? So we get this theorem in here that these two sets are equal, right? So the set S is equal with the set AS. So if I multiply everything in here and in here, for example, this with this, and I cancel all the good numbers, I get Fermat's little theorem. A to the p minus 1 is congruent with 1, right? Because you can cancel on both sides by the p factorial, p minus 1 factorial. And then I guess we also have this idea of this idea of inverses, right? So what's going on with the inverses? So basically, let's say that I had some equation that looks like this: AX is congruent with B. Then one thing I can do is I can multiply by A inverse and by A inverse. So what's happening is this two are going to disappear. So I get that X is going to be congruent with B divided by A mod B. When I say B divided by A, it's not really a fraction. This is actually what this means. It means B times 1 over A, which is B times A inverse. So it means that I multiply B by A inverse. I don't divide B by A, but I write it like fractions because it's going to behave like fractions, but they're not fractions. But same things you do for fractions, you can also do for them. We're going to prove that. All right, cool. So yeah, so I guess if you look, you look mod 7, I guess what is going to be the modular inverse of 3? Well, you can try them all one by one. And we actually already saw in the beginning of the class that 5 is the inverse of 3, right? So 3 times 5 gives you 1. So 5 is the inverse of 3. So whenever we have an inverse of A, we write it like A minus 1 or 1 over A. So for example, in here, A over B just means A times, B inverse. Okay, so now I guess a couple properties. So like 2/3 is actually going to be 2 times 3 inverse. Well, what is 3 inverse? 3 inverse, we already discussed that 5 is the inverse of 3, right? So this is going to be 2 times 5, which is congruent with 10, which is going to be congruent with 3 mod 7. Now, what about 3 times, 8? Well, this is going to be 3 times 8 inverse. And now actually 8 inverse is going to be 1 inverse. So actually you can, if for example, if A is going to be congruent, so here's a property. If A is congruent with some remainder R, then A inverse is going to be congruent with R inverse mod n. Mod n. Why is this the case? Well, because I guess if I look at like this thing in here, if I multiply so if I had, A is congruent with R, so if I multiply by A inverse and I multiply by A inverse, what do I get? I get that this is going to be congruent with 1 mod n. So I guess what do I get? I get that I have that this thing in here, when I multiply it with R, I'm going to get 1. So it means that this thing in here needs to be R inverse. It's the inverse of R, right? So I get the property A inverse is R inverse. So by using this property, for example, what can I get in here? So if I look at like 8 inverse, well, so basically if I wanted to look at like 1/8, so I look at this mod 7, right? Mod 7, then I see that 1/8 is going to be 8 inverse, which is going to be, well, 8 is going to be congruent with 1 mod 7, right? So I guess what I'm trying to say is that this can be written as like 1 inverse, which can be written as like 1/1. So yeah, I guess if you had that like 1/9, you can say that this is going to be congruent with 1/2 mod 7, which when I write it, because 9 is going to be congruent with 2, right? So because 9 is congruent with 2, I can remove the 9 and I can just like write 2. So basically the inverse of 9 mod 7 is the same as the inverse of 2 mod 7, right? So I guess in this case, I'm going to have that I can take this 8 inverse, I can write it as 3 times, 1 inverse, but the inverse of 1 is 1 itself, so I can just forget about this. So it's just 3, right? And now how about 20/46 mod 7? Well, you see that 20 is going to be congruent with -1, 46 is going to be congruent with 2, so the entire thing is going to be congruent with 1, -1 divided by 2. Well, but what is the inverse of 2? We see that 2 goes with 4, right? 2 times 4 is going to be 8, which is congruent with 1 mod 7. So basically, if somebody gave you 2 inverse, which is, 1/2, this is actually the inverse of 2, which is 4, right? So basically, I can take this and I can replace it as like 1 times 4. So it's going to be congruent with -4, which is congruent with 3 mod 7. Yeah, so basically, that's how these fractions in modular arithmetic, they work in here. Okay, so I guess now what could we do next with this, right? So I guess if I had AX is congruent with B, I can multiply by A inverse, as long as A and P are good, right? A is not 0 mod P. If A and P are good, I can do that, and I can get X is going to be B times A inverse. Yeah, so for example, now the modular inverse doesn't always exist. So for example, if you pick a bad number, so 2 is bad to 6. So if you look at 2 and you try to combine it with anything, you're never going to get 1, because 2 and 6 are bad, right? So we discussed that. If 2 numbers are bad, they're not going to have an inverse. So if you guys look at this example that we discussed in here, right? If A and N are bad, then I cannot have an inverse, because if I had some inverse, then this would need to be a multiple of D, this would need to be a multiple of D, but this is not a multiple of D, right? So not possible to have an inverse. So for example, if I had 2 and 6, it wouldn't work, because both of them are bad because they have common divisor 2, but 1 is not a multiple of 2. Okay, cool. And now there is this idea that inverses behave like fractions. So here is the trick. So for example, for fractions, you could do this thing. If you write 2/3 plus 3/8, you can add like them to the common numerator, right? So you can amplify this by 8, amplify this by 3, and then in here you're going to get 16 plus 9 divided by 24, and you're going to get 25/24. Turns out that you can do the same thing with modular inverses. So for example, if you had 2 times 3 inverse plus 3 times 8 inverse, turns out that this would be congruent with 25 times 24 inverse, because, well, if you look at this thing is exactly this, right? But then this is going to become this, but then this thing in here is this, right? So basically this, you can also like do modular inverses with fractions. Now we haven't proven this, so how can we show that this is the case? Well, at least let's check it. Let's get some intuition. So look at this. What is this going to be mod 7? So if I look at this, 2/3 plus 3/8, this is going to be just 2 times 3 inverse, 3 plus 8 inverse. So mod 7, right? So because the inverse of 3, we say it was what? 5, right? Sorry, 3 times 5. Yeah, so the inverse of 3 is 5, so I can replace this with a 5. And the inverse of 8, well, I guess 1 over 8 is going to be congruent with 1 over 1 mod 7, which is going to be congruent with 1, right? The inverse, so 8 is going to be congruent with 1. So I can just replace this, replace it with a 1. So I guess this is going to be 10, which is congruent with 3. And this is 3, so I get 3 plus 3, so this is congruent with 6. So I get that this all is congruent with 6 mod 7, right? Mod 7, this is congruent with 6. But now how about this stuff in here? Well, if you look at this, well, 25 is going to be congruent with 4, and 24 is going to be congruent with 3 mod 7, right? So this is going to be 4 divided by 3, which is 4 times 3 inverse. But again, we discussed the inverse of 3 is 5. So if I remove it, replace with 5, I get 4 times 5 is 20. And 20 is congruent with 6 mod 7, right? So we got that this one is also congruent with 6 mod 7. So it turns out that, I can do the same stuff with fractions. So if I had some like big stuff in here, 2 times 3 inverse, 3 plus 8 inverse, I can write them as fractions, bring them to the same numerator, get this final thing, and then write this as 25 times 24 inverse, and then compute this final thing. So basically, modular inverses, they behave like fractions. You can do the same stuff as fractions. They're not fractions, but they work exactly like fractions. All right, so let's see what can we do in here. Inverses behave like fractions. So I guess we discussed this. How can we prove that the inverses behave like fractions? Well, I guess let's look at I guess A over B, C over D. So if you look at like this example in here, so basically what the statement is saying is that if you look at like this thing in here, this is going to be congruent with this. Why is that the case? So, well, let's look at A over B and C over D, right? So if I look at let's look at this property. So if I had, A over B plus C over D, well, what is this? This is going to be congruent with, I guess, A times, what I mean here is that this is A times B inverse plus C times D inverse, right? Okay, so now look at this thing in here. So if I had this thing in here, well, what is one thing I can do? I want to have some common stuff that I can take out. So if you look at this has some D, this has some B. So B and D are the things that I want to work with. So one thing I can do is I can add, B inverse times B, which is just, just a 1. And then in here, I can add D inverse times a D, which is again just a 1. And now I can take, B inverse, D inverse in front of the parentheses. So I can basically rewrite this as like B inverse, D inverse. And now what am I going to have inside? Well, if I take B inverse, D inverse in front of the parentheses, it's going to go in front of the parentheses. This one's going to go in front of the parentheses. In here, I'm going to be left with AD. Plus, I guess in here, I'm going to be left with CB, right? So now if I actually were to simplify this, I get that this thing in here is going to be congruent with, I guess, now if you look at this thing in here, this is B inverse, D inverse. This is the same as like BD all inverse, right? In here, so I can rewrite this as like AD plus CB divided by BD. Yeah, so basically, yeah, we got that this thing in here is exactly the same as this thing. And how did we prove it? We multiplied by this thing that's a 1 on both sides, and then we just took in front of the parentheses. B inverse, D inverse, B inverse, D inverse, right? It came in front of the parentheses. And then we just like wrote this thing as like a big, yeah, the inverse. So basically, if I were to multiply for example, I asked you, what is, I work mod 7. So question is, what is 3 inverse times, I don't know, like 2 inverse mod 7. Well, then one thing you can say that this is just going to be 6 inverse. So you can figure out, if you tell me what the inverse. So basically, I don't need to compute each one individually. I can also like write them like this. Why can I do this property? Well, because like, okay, look at this. So if I had, I have that A, I had, let's say that I had this thing here. So A times B. So, well, let's say that, I have A times A inverse is going to be congruent with 1. And I can also multiply this. So I can multiply and I can rewrite this as like times B inverse is going to be congruent with, well, this is 1, this is 1. So this entire thing is congruent with 1. But I can also rewrite this as like AB times A inverse, B inverse. But also I know, so, okay, so what do I have? So I have this, but I also know that AB times AB inverse is also 1, right? So I know that these two are the same, so it means that these two need to be the same. So if these two are the same, mod n. Now if A and B are good, mod n. So the only way I can get inverses is if they're good. So now if I just focus on this two, and if I remove the good stuff, I get that these two have to be congruent. Okay, cool. So hopefully these ideas with modular inverses are clear in here. So now I guess what else can we do? So yeah, this is basically the proof that the property works. And also we have stuff like this. So for example, if I had A over B, C over D, then I can also like write them. This is going to be A times B inverse, C times D inverse, and I can pair them A, C, and B inverse with D inverse, put them together, and then put them under a big inverse. And I can rewrite this like this, right? So basically this property also works. So here's a couple examples. So for example, if I had 2 times 3 inverse times 3 times 8 inverse, then this is going to be 1 times 4 inverse. So you can write it like this. 2 times 3 inverse, 3 times 8 inverse, mod 7, right? So what is this? Well, I know that 8 inverse is just, 1 inverse, which is just 1 3 inverse was equal to, I guess, what was it, 5, right? So I had that this is 10, which it gives me a 3, and then this one is just a 3, so I get that this thing is 2. But now what about, 1 4? This is going to be 1 times 4 inverse. Well, the inverse of 4 is going to be 2, right? 2 times 4 is 8. So I can just remove this thing and get 2. So I guess both of them give me 2. So this formula works perfectly in here. Yeah, so this is basically how the modular inverses work. Here's a couple, practice problems. This problem is trivial. We already discussed it with Fermat's little theorem. So like one simple way to get a modular inverse is to, recall Fermat's little theorem. So if you had, a to the power p minus 1 is going to be congruent with 1 mod p. But you can also say that this is going to be a times a to the power p minus 2. So you can think about this as being some number k such that, I'm going to have a k is going to be congruent with 1 mod p. So you can think about this k, which is basically, this is a modular inverse, right? Which is basically a inverse, which is basically 1 over a. So one very easy way to get, a inverse, which is congruent with 1 over a, it's also congruent with a to the power p minus 2 mod p. So yeah, so this is like also another like very simple way to get a modular inverse is by using Fermat's little theorem, as long as a and p are good numbers to each other. Yeah, so that's basically it. And now basically, yeah, we discussed Wilson's theorem, and the modular inverses, they go in pairs. So there's gonna be some yeah, and we got Wilson's theorem. And I guess you can read and work through some of the problems in here. They used Wilson's theorem and get some practice. And now I guess there's also like the more general case and the general inverses, right? When you don't work mod p, but you work mod n. And we saw that mod n, this is also true. But we actually, when we wanted to prove, when we looked at the product didn't quite work. So we only looked at the good remainders, right? So we, instead of working with the set A, S, and we created the set, a new set, like the good set. So basically, if you start with this set in here that has all the remainders, you keep only the good remainders. So if you look at like this thing in here, so this Sn, this is the same as our definition of Gn, the good sets, right? So if you multiply all the numbers, you got, I guess you get all the good numbers, you can simplify them. So you get Euler's theorem, right? A to the number of good remainders, which we discussed, called phi of n in the past, is going to be congruent with 1 mod n, right? So yeah, we have Euler totient function that counts how many good numbers are there between 1 and n. Yeah, we'll actually take a better look at like Euler's totient function in the next class in the future. But I guess for now, I guess we also want to discuss the idea of general inverses, right? Which is also related to Bezout's theorem. So basically, the question is, can I find an inverse, mod n? And normally, if n is not a prime, you can't. But one exception is when a is a good number. If a is a good number, then there's always going to be an inverse. So, but if a is a bad number to n, it's not, there's going to be no inverse, right? So for example, if I had 3 and 9, 3 is bad to 9, so 3 doesn't have an inverse, because you can try 3 with all the numbers and you never get 1. 3 times 1, 3 times 2, 3 times 3, all the way. You don't get any 1, because all the numbers that you can get are going to be multiples of 3, like they're going to be like all multiples of d, right? So inverses don't always exist. If a and n are a bad pair, there is no inverse. There's only inverse if a and n is good, right? So they say that a has an inverse if and only if a and n is a good pair, if a and n are relatively prime. If they're not relatively prime, if they're a bad pair, there is no inverse. And there's a bunch of practice problems in here. So that's basically going to be homework for you guys to try and solve them. So now I guess that's kind of like the main thing that's important here on modular inverses and Wilson's theorem. There is like some extra stuff with like orders and polynomials in modular arithmetic, but we don't need that for now. So I guess, yeah, we will take a break here. So if you want to read more about this, I put this in the chat. I put Wilson's theorem in the chat. One thing that's missing is Bezout's theorem. So let me also put Bezout's theorem in the chat so you can see this as well. Yeah, so I guess this is kind of like some of the most important things. Yeah, so I think this is kind of like some of the main ideas that I wanted to discuss with you guys. Yeah, and then I guess we can take a break here, and then in the future class we're gonna look into more details at squares and yeah, modular arithmetic with squares and also Euler-Torsion function. Okay, so yeah, thank you everyone, and take care. See you in the next class.